Hello, Biology 230 students at Tuskegee University. This is Dr. Griffin with the fifth video for the Chapter 5 lectures of Module 3. Remember, Module 3 consists of both Chapters 4 and 5 in your Campbell Biology textbook. Dr. Whittington produced the lecture for Chapter 4, and I have done a set of videos, 5 videos. This is the fifth and final video for Chapter 5 portion of Module 3. This video will focus on lipids. Lipids are not actually true macromolecules, so the book kind of just put them on alongside the other true macromolecules. Lipids are not true macromolecules mainly because they aren't really that big, number one, especially compared to nucleic acids, carbohydrates, and proteins in size. And they're also not true polymers. As we'll see in the next set of slides, lipids are mainly just a long chain of carbon molecules attached to hydrogen atoms. The main characteristic of all lipids, I'm going to say all again, is that all lipids are hydrophobic. This means that they mix poorly with water. They are hydrophobic, they are fearful of water, they do not want to mix and dissolve in water. The first group of lipids that we'll discuss are fats. They're also known as triacylglycerols. Okay? Tri meaning 3. Acyl just means that there's fatty acids in it. So there are in fact 3 fatty acids. And fatty acids are nothing more than just a long chain of hydrocarbons. So that's CH bonded to each other. And a molecule of glycerol. That is what a fat is. 3 fatty acids and 1 glycerol. Saturated fats are saturated with hydrogen. Okay? There are no double bonds. So you have the maximum amount of hydrogens present in a molecule of saturated fats. Unsaturated fats, however, have multiple or at least one double bond present. They are not saturated with hydrogens. And one example of unsaturated fats are trans fats. You probably have heard about trans fats in the news, mainly because they're deemed to be very bad for you. However, trans fats were first used because of their chemical nature, in that they are very stable, and yes, as we have learned, very bad for us because they're one leading cause of atherosclerosis, which could lead to multiple heart and blood pressure issues, as well as just increasing rates of obesity in the country. But trans fats were used to extend the shelf life of processed food. And that has to do with disorientation matter. Hold on one second. We'll wait for it. Should be coming. That's right. It's another blast time. In fact, we're now for a organic chemistry blast. As you see here in this white box in the right portion of the screen, molecules can have 2 different orientations, especially hydrocarbon molecules. The first is known as a cis orientation. Whenever you have a double bond, you can imagine here that there is free rotation. This H could be up here, or as shown here, it could be up here, or down here, or up here. Across from the double bond, if 2 or more atoms on the same side of the double bond and are really close to each other, as shown here, they're referred to as being cis in nature. However, across from the double bond, if they're on 2 different sides of the double bond and are very far apart, if you will, from each other, they're known to have a trans orientation. Well, multiple molecular and chemical studies have shown that molecules and chemicals with lots of trans orientation in their compounds or molecules are very stable and are hard to degrade. So again, trans fats, with all their long hydrocarbons in their one glycerol group, if they have multiple double bonds, or very few double bonds, and are able to stay apart from each other, very far apart, they're known as trans, giving them their very stable ability or feature. And here's one hydrocarbon, one trans fatty acid. Okay, doesn't have a lot of double bonds. And you can see here, this hydrogen is on the other side of, well, they actually drew the circle in the wrong place. This hydrogen here is on the other side of this hydrogen, as well as this hydrogen is on the other side of these two sets of hydrogens. Okay? So whenever you're going from top to bottom, or top to bottom, or bottom to top across this double bond, it's a trans configuration or orientation. And the trans has a very stable half-life or stable shelf life, which, yes, allows for the food to stay good, in quotation marks, on the shelf, but it also allows for that fat to be hard to degrade in our arteries, clogging them up and causing atherosclerosis. Another main lipid that you'll want to be concerned with, besides fats themselves, is the group of phospholipids, or phospholipid. Phospholipids are amphipathic. Maybe we see that portion of the word in amphibian, meaning you're able to do two different things. Well, phospholipids are amphipathic because they contain both hydrophobic and hydrophilic regions. They contain a long stretch of fatty acids, shown here in this space-filling molecule. And here are the fatty acids here, this structural formula configuration. This is the hydrophobic portion, or the hydrophobic tail of phospholipids. Now, phospholipids, being true amphipathic in nature, also contain this phosphate group here, shown in yellow. You can see it also in this space-filling model here. This is where the hydrophilic region is. Remember, phosphate groups, this group of phosphate or phosphorus connected to 4 different oxygen atoms, is negatively charged, and thus any charged ion will most likely be hydrophilic in nature. Therefore, the phospholipids have this hydrophilic head due to this phosphate group, and a hydrophobic tail, given the fatty acids in the tail portion. And here's just a way of phospholipids are symbolized with this little circle with the hydrophilic head due to the phosphate group, and the hydrophobic tails due to the fatty acids. Phospholipids are a key component of the plasma membrane that we'll discuss in more detail in Chapter 7, this textbook. The last lipid that we'll discuss belongs to the group of steroids. Okay, steroids are lipids with 4 fused rings. And more specifically, steroids are either cholesterol itself, shown here in this image. This is the structural formula for cholesterol, or any derivative of cholesterol still containing these rings. So 2 examples of cholesterol or steroids are estradiol or estrogen, and testosterone. Both of those are steroid hormones that are derived from cholesterol. After this module, you should be very comfortable in doing the following. Recognize the monomer subunits in a large polymer. Comprehend the mechanisms in the assembly and disassembly of polymers. Identify monosaccharide based on a given molecular formula. Identify key functional groups: hydroxyl, phosphate, carbonyl, carboxyl, sulfurhydryl, amino, etc. They're main ones that are highlighted in your book. You should also be able to identify nucleotide from a nucleoside, as I discussed in earlier videos, as well as key components of a carbohydrate and a protein or amino acid, particularly. Understand the structural and functional relationships in macromolecules and lipids. So what do these hydrocarbons do for carbohydrates? What do the carbohydrates do for lipids? What does the phosphate do for phospholipids, etc.? And lastly, compare on a structural level different forms of fats, nucleotides, simple sugars, and amino acids. And this is kind of asking the earlier point of understanding the structure and functional relationships in a different way. So if we were to change the structure of these different macromolecules or the monomers that they're made up of, how would that affect their function? Well, that's it for this video series on Chapter 5 in your Campbell Biology textbook. This is the video lectures for Chapter 5 and all the video series lectures for Module 3, which is Chapters 4 and Chapter 5. If you have any questions, if you can't do these objectives, if you're having a hard time doing the practice tests that I posted on Blackboard, feel free to email me or post questions on the discussion board. That's what it's there for. Stop by my office hours, which are just Monday, Tuesday, Friday from 2 to 4 p.m., or email me to make an appointment. Thanks and have a great day, and I look forward to seeing you on campus and in class. This is Dr. Griffin, signing out.